This is a YouTube channel about BASE-12 math and specifically BASE-12 geometry. So in this video, I'm going to be introducing you to the information that's in this book that I wrote recently called Understanding BASE-12 Math, How to Draw the Perfect Circle Using Dozenal Geometry. Alright, so by the end of this video, you will understand the important difference between BASE-10 and BASE-12 geometry. You will know how to build a BASE-12 Cartesian plane. You will be able to divide the circle into 360 degrees perfectly and precisely. You will be introduced to a new geometric pattern, a BASE-12 dodecagon, the BASE-12 dodecagon, and you will be introduced to a new number which is derived from dividing the diameter of this dodecagon into its perimeter, which eventually becomes the circumference of a circle. A perfect circle. So as simple as that last statement sounds, it's actually controversial because we know that the official definition of a circle, or the official stance towards circles in general, is that there is no such thing as a perfect circle. So we're going to revisit that definition at the end of this video, and you can ask yourself, have we drawn or created the perfect circle? Alright, so the first thing that we want to do is let go of the idea that the only difference between BASE-10 and BASE-12 is how we group our numbers. And that a number like 29, where we have two groups of 10 plus 9, becomes a number that looks like 25, where we have two groups of 12 plus 5. So we arrange the groups or the structure of the number, but ultimately underneath it's still the same amount of whatever it is that we're counting. So that's a very simple and almost childlike way of looking at the difference. So we're going to completely let that go, and we're going to look on the other side of the decimal place. So the length of 1 is the same regardless of the base, but it depends on what base we're in as to how we divide that length of 1. So here we have the length of 1, and on the bottom we've divided it into tenths, that's BASE-10, and at the top it's BASE-12, and you can see that there's 12 little sections, and those little sections are shorter than they are in BASE-10. So that's the real difference between BASE-10 and BASE-12. It's the size of the decimal place, or the length of those little sections. So the result of that difference is that the BASE-12 Cartesian plane has a denser grid. There's more horizontal and vertical lines, and so there's more lines and there's more lattice points where those horizontal and vertical lines are crossing each other. Here there's an example of the two Cartesian planes, one on top of the other, and you can see that the points where the lines are intersecting each other lines up differently. So that's the real difference between BASE-10 and BASE-12. So what I'm going to do now is introduce you to a geometric pattern. So it's a type of dodecagon, and we'll first look at it without any base in mind at all. We're just going to look at it as if I was describing it to you on a piece of graph paper. So this is what it looks like. We will put our X and Y axis there just to create some structure. And then there's 12 points that we're going to use to define this polygon. So we're going to travel along the X and Y axis the distance of 13 little squares and make points, 1, 2, 3, 4. And then we're going to travel along the X and Y axis the distance of 12 points. And then we're going to go up and down seven little squares and make points, and to left and right. So we have a total of 12 points, and those points we now just connect with lines, and we have this polygon right here. So I would be able to give you this drawn on a piece of graph paper and ask you, how long is the perimeter? So when we look at this 12-sided polygon, we can see that the four corners are made of isosceles triangles, where either side of the right angle is 0.5, and so the length of the hypotenuse is 0.5 root 2. And the other 8 triangles are 3, 4, 5 triangles, where either side of the right angle is 0.3 root 2 and 0.4 root 2. So the hypotenuse is the length of 0.5 root 2. So we can see that all 12 sides of this particular polygon are the length of 0.5 root 2, and all of those lengths and triangles are defined by specific lattice points on the Cartesian plane. Alright, so somebody's handed us a piece of paper with this written on it, and they've asked us, what's the perimeter of this polygon? So we would look at that and go, well, we know all the sides are the length of 0.5 root 2, and we know there are 12 sides, so we're multiplying up by 12. So we know 5 times 12 is 60, so 0.5 times 12 is going to be 6 root 2. So that's our answer, and in most cases it would be right. We all do our math in BASE-10, but in this case we haven't actually defined our one, so it's still a little bit of a question. What is the base that this drawing is in? Where are we going to draw the length of 1? Because that makes a difference as to the length of the polygon. All right, so the first thing that we're going to do is look at a base 10 Cartesian plane, and we define the length of 1 by 10 little squares. So now we're going to switch it up and draw the same diagram on top of a base 12 Cartesian plane, and this is what that looks like. So now you can see that the length of 1 actually lands on the dodecagon, or the dodecagon lands on the length of 1. So what's the big deal with that? Why is it so important that it lands on the length of 1 as opposed to just floating somewhere else? And it's because when it's floating somewhere else, it's there, but there's lots of places where it's not. When it lands on the 1, that means that every point on the x-axis, no matter which one it is, it's connected to this dodecagon pattern. If you were to multiply 1 by any number, then you could multiply the proportions of this dodecagon on all the points that define it, and you'd realize that it's completely anchored on the Cartesian plane in a way that it isn't in base 10. Here we have changed the size of the decimal places, and you can see one dodecagon is definitely larger than the other. Okay, so we have a large version and a smaller version. Now we'll go back and just see what exactly the length of the smaller version is. Okay, so now we're back at the same question, 0.5 root 2 times 12, but we're doing it from a base 12 point of view. Although I really want to keep this easy for you, so let's maybe still kind of balance between base 10 and base 12. We can do it in base 10 still, but making sure that we are talking about twelfths. If in base 10, 0.5 isn't 5/12, it's basically 5/10, isn't it? So we want to know what 5/12 root 2 times 12 is. So if we do it from a base 10 point of view, we can just say, look, that's 5/12. 0.5 root 2 in base 12 does equal 5/12 in base 10. So keeping it simple, I hope, 5/12 root 2 times 12, well, we just cancel the 12s, and then we're left with 5 root 2. Okay, so now we've gone over the Cartesian plane. I think we understand the difference between the base 10 and base 12 Cartesian plane. We know how the base 12 dodecagon is sitting on the base 12 Cartesian plane. So that's 2 of the 3 geometric components that we need to construct our diagram for 360 degrees. So there's one more geometric pattern that we need, and that pattern is called the Dozenal diagram. So this is the diagram that enables us to actually create the Cartesian plane, as well as divide the circle perfectly into 360 degrees. It's the backbone, really, for the structure. So first thing I want to do is show you how to draw and create and build this Dozenal diagram. All right, so the only thing that we need to create this diagram is a blank sheet of paper, a compass, and a straight edge. So we put down our paper, we set our compass to a specific length that we don't change throughout the process of creating the diagram. We stick it in the paper, and we create our first circle. Then we put our compass onto the circumference of the circle that we just drew, and we draw another circle. Then we put our compass down on the point where the 2 circles are intersecting, and we draw another circle. And we continue that process going all around the circumference of the first circle until we get back where we started. And that's the first part of our diagram. Then we take our straight edge and we draw lines through the center, connecting all the points that we just created. And this is what we get so far. So we'll just stop here and take a look at our diagram. Here we've divided the circle into 12 equal sections. So I think this is basically showing us how the base of the circle is created, or how the base 12 version of the circle emerges from the geometry. We're just interacting circles of all the same radius, and we are left with the diagram that perfectly divides the circle into 12 equal sections. Okay, so the next part of the diagram, we just keep doing the same thing. We look at the point that's been defined by one of those lines going through where it intersects the circle at a point where the compass hasn't been yet. We put our point of the compass down there, we draw another circle, and we repeat the process 5 more times, so 6 in total, until eventually we have 12 circles all anchored on the original circle that we drew first. Then we continue the process of drawing straight lines through the center of the circles, going all the way around, using the points where they intersect. The lines go through the middle of the diagram, and that's how we get our Dozenal diagram. So the next question is, how do we use this diagram to create our Cartesian plane? So now we have to adjust the length of our compass. We're going to expand it a little bit, adjust it to the length of square root of 2. So we get the length of square root of 2 by drawing some horizontal and vertical lines that parallel the x and y axis. So these points are already determined within our diagram, so you can see what that looks like here. We set our compass and we draw that circle. It's got the radius of the square root of 2. You can see the little triangle here. We're setting the radius of our first circle and all those initial circles that we drew to the length of 1. So now we've got these parallel lines, and each of those is the distance of 1 from our x and y axis. Now we're going to travel along the x-axis the length of 1, put our compass on that point, and now we make marks, and now we've created our Cartesian plane. Okay, so now we're going to look at the geometry of the dodecagon and get more familiar with this geometric pattern. But before we even start that, I want to just give you a little pep talk that because of the math, I'm going to be introducing some new symbols to you. Down here at the bottom, we got X and A, which equals 10, and this L, which could be a B, and equals 11. And you're going to see numbers here. I got a 9, 6 up here coming up. And I know when you look at that, you already know where it fits on the Cartesian plane if you were in base 10. You know, anytime you see a 9, you're kind of close to the end. A 6 is a little bit past halfway. Here, it's different. So you got, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, 10. All right, I just want to clarify something. That's a mistake. There is no 10 in base 12. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, do for a dozen, or 8, 9, dec, L, do. So do looks like a 10, but it represents a dozen in base 12 math. Or point 9, point A, point B, 1. When you see a 6, that's the half in base 12. So it's a little bit of adjustment to make. So the actual geometry is very simple, and I think if we were already in a culture that was using base 12, it's a high school level math really, but in base 12. So the real challenge is just refocusing your brain when you see all these funny numbers and realizing that that's the jarring part where you have to kind of think. So don't try to do too much of the math in your head right away is my recommendation. Just let it go. And so that being said, I'm going to be giving you a lot of fractions as well as we kind of transition from base 10 to base 12. The first ring of the diagram for 360 degrees is the main focus for this video so that you really understand that structure, because once you get that, the rest of the rings of the diagram, because it's a big diagram with lots of rings, it all follows from that first structure. That structure needs the structure of the dodecagon understood first. So that's where we are now. We're building the mathematical structure, and the fact that we're doing it on the base 12 Cartesian plane gives us, it's already built in, that 12. So there's 12 everywhere. So the 9 is 3/4, 6 is a half, 4 is a third. Okay, so the base 12 dodecagon, the first thing we want to know about it is that it's built in units of square root of 2. So we've already looked at the perimeter, and we saw that it was built in units of 0.5 root 2. And so now we're going to look at the diameter, which is built in units of 0.96 root 2. So the diameter is going to be the 45-degree line. So normally with the diameter of a polygon, you go from outer point to outer point, but in this case, we're sticking with the square root of 2 and we use the 45-degree line, because ultimately it's not so much about the polygon, it's about the circle. So keep that in mind. So 2 times 0.96 is 1.7, so that's the total diameter of the dodecagon. And then half of 0.96 is 0.49. Okay, remember. So again, I'll just give you the fractions there. So 0.5 is 5/12. 0.96, that works out to 114 1/44. And so half of that, 57 1/44. So it's not too crazy. And then you'll be seeing the letters A and B. I use those mostly in my book, and sometimes with my writings I use this symbol called dec and L. So dec is for a decade, DEC, like 10, right? And L, start at the beginning of the word 11. And lastly, the dodecagon is a repeating pattern. So the second ring of the pattern, all the sides and the proportions are 2 times out of the first. So the perimeter will be A, will be the length of A root 2. 2 times 5 root 2 is A root 2. And then the diameter will be 2 times 1.7 root 2. Then the third ring of the diagonal will be 3 times that, and then the fourth ring of the polygon will be 4 times that, and so on. Okay, so we're going to be going eventually to the fourth ring of the dodecagon pattern to build the structure for the first ring of the diagram for 360 degrees. But we want to look a little more deeply at the structure of the BASE-12 dodecagon first. Okay, so what we want to do first is look at the relationship of the dodecagon to the 30, 60, 90 triangle. And just see what the angles, what's going on here with this triangle. It's defined by the length of 1 and then up 0.7 here. Okay, so we have our dodecagon. We got this, the 45-degree line going along. It's got the length of 0.96 root 2. We have these 3 sections of 0.5 root 2 that comes down here. But we want to look at this triangle compared to the 30, 60, 90 triangle. So first of all, what are these proportions? We know 1.7. If we want to convert it to a square root, actually it's down here, 0.7 squared is 0.41. Actually, what I was doing here, I was just looking at the 3, 4, 5 triangle that I used as an example, and there's also another triangle on the other side of that, which has the dimensions of 0.1 and then 7. So if we square 0.1, we get 0.01, and 0.7 squared is 0.41. So you add those together, you get 0.42. So the square, so this again is, so the hypotenuse is the square root of 0.42. So is that the same as 0.5 root 2? So we see here 0.5 squared is 0.21. So 0.21 times square root of 2 is square root of 0.42. So 0.5 root 2 also equals the square root of 0.42. And so the entire perimeter of the dodecagon is the square root of 4 do 2. Remember, we're multiplying by a dozen. It looks like 10 in BASE-12. Okay, so back to this triangle. What's the relationship of this triangle to the 30, 60, 90 triangle? So this, again, these dimensions are 1 and then square root of 0.41 for this side, and then the hypotenuse square root of 1.41. So here's the special right triangle with the square root of 3, 1, square root of 4. So we're going to convert the base to the length of 1 just to see how close they are in similarity. So square root of 3 divided by 1 is 1. By square root of 3 divided by square root of 3 equals 1. 1 divided by the square root of 3, this is the important side, is square root of 0.4. So that's BASE-12. 1 divided by 3 is 0.4. So square root of 0.4, and we see that this is 0.4 and that's 0.41. So this is a little bit bigger. So we go back here, we see that this, the line for the dodecagon is a little bit higher than the line for the 30-degree line, that angle. So there's a little bit of a gap in there. Of course, it's the same on this side, a little bit of gap. So we see that this triangle formed in here is just sitting inside of the 30 and 60 degree lines. So given that this is the length of 0.5 root 2, and all of these lengths we know are the length of 0.5 root 2, it makes sense, or it's sort of geometrically logical, that we should be able to take that angle, that sort of squished aspect, and rearrange it so that it also has the same relationship to here. It would be the 15-degree line. The 15-degree line, and that would have the same relationship as this section to the 45-degree line, and there'd be an empty space between them. We can do that all the way around. So that makes sense that this doesn't reach the 30-degree line, because if it did and all these were the same length, then this thing would have to be already a regular polygon, but it's not. It's an irregular polygon with sides that are all the same length. So it has this dodecagon, the first ring is that sort of squished, the overall pattern is like a squished aspect to it, where these points here are closer to the center than these ones here. This length is the square root of 1.41. This length here, this point is defined by this point, so 1.1. So 1.1 squared equals 1.21. So this is the square root of 1.21. This is the square root of 1.41 as far as the distance from the center. So I'll just show you quickly what that looks like in the book. You can see how close these two lines are. and that you really have to zoom in to see the gap. And I've given you the conversion of the square root of 0.4. It's I think 0.6b, and then it goes on. So that's what that looks like, just so you're aware of how close those two lines are. It's hard to even draw them with a pencil, but of course they get wider the farther away we go from the center of the Cartesian plane. Okay, so now we're going to use the points that we were just talking about in the last section to draw two circles with those points defining the radiuses, or the radii. So we have a circle with the radius of the square root of 1.41 and a circle with the radius of square root of 1.21. So I'll show you a quick picture of what that looks like. And so we're simply going to first start by figuring out the area that these two rings define. So we know the area for a circle is pi r squared, so we'll just subtract the area of the smaller circle from the larger circle. So that's going to be 1.41 subtracting from that 1.21, and we get 0.2 pi. You know, we're squaring the square roots. 0.2 pi. So we have two circles that are going like this, and then the area inside them, complete circle, is 0.2 pi. So we know which points are defining those. So now we're going to look at a middle circle. So that point is defined by where the 45-degree line is intersecting the dodecagon, and we know that radius is, well, we know that it's 0.96 root 2, so we're going to convert that into square root of 1.306. So we do that by squaring 0.96, you get 763, so the square root of that, square root of 2, gives us square root of 1.306. So now we've drawn a radius right in the center. So how centered is that? Well, we'll do the same process. So we'll define the area of this ring specifically, the outside, and then define the area of the inner ring. So the outer ring, we're going to subtract from 1.41, 1.306. So we're this is base 12 math, or Dozenal math. So 6 from a dozen is 6, 0, 3 from 4, 1. We get 0.106 units of pi for the area of this outside ring. And then for the inside, we do the same thing, but the other way around, 1.3, subtracting 1.21 from 1.306. So you can see 0 from 6 is 6. You know, 1 from a dozen is 11, or L. So I put our symbol for L there. And then a 0, so we have 0.0L6 as the area of this inner circle. So we can figure out the difference between those two areas simply subtracting one from the other, the smaller from the larger. And so 0.0L6 subtracted from 0.106 gives us an answer of 0.01 pi. So very little difference between these two areas, and the outer one is slightly larger than the inner, which follows when you think about the growth pattern of a circle. It keeps getting larger as it goes out. Still, so that's just to point out the main point we want to take away from this is how centered that middle circle is, that middle ring. And that is actually that's the circle, that's our main circle. That's the circle that we're using and we're building upon as we build our diagram for 360 degrees. It's our main circle. That's when I'm talking about dividing the circle and all the points on the circle. It's the circle that's always defined in units of 0.96 root 2, and then that's basically the radius. So the diameter is always going to be 1.7 root 2. So these are key numbers in the overall structure of the diagram, and so that's something to keep in mind. Okay, so now we have all the geometric ingredients that we need to do the process of converting the geometry that's kind of wrapped around the 45-degree line and transferring it to the 15-degree line. So what I mean by that is we have our Dozenal Pisces diagram set up, generating all the degree lines. We have the BASE-12 Cartesian plane as our anchor, defining the specific lattice points, specifically around the units of square root of 2. So we're working up here from specific lattice points. then we know that we can draw circles defined by these lattice points that then intersect or cross the 15-degree line. So now we can use all that to basically go through a process of taking this information and transferring it down here. So what we're going to do is we take our compass, or the computer equivalent of a compass, to set a circle with this radius here, and then we simply put our compass on the point where the 15-degree line is intersecting this inner circle. So this is again our circle with the 0.96 root 2 radius, and we just take our compass, put it there, we make marks on the outer circle, just like what's already happening here. These are all specific lattice points, and so this isn't a lattice point. These aren't lattice points, but they're still points. So when I say the diagram is anchored in units of square root of 2 on the Cartesian plane, that's all happening up here, and we're able to transfer that information down here. And we know that this is all floating inside the 30 and 60 degree lines. So I'll add that up here like that, 60 degrees. And you can see I've actually written the BASE-12 version of these, just to keep in mind that we are working on the BASE-12 Cartesian plane. So we set those points, and then we draw a line across. So now we've got a line that is perpendicular to the 15-degree line. Everything's exactly the same as it is there up on the 45-degree line. So that's the process that we use in the creation of the diagram. Throughout the process of creating the diagram for 360 degrees, we're transferring this information, using that as our anchor. When I say this whole diagram is anchored on the Cartesian plane, this is where that's happening, using points that are defined by the placement of the lattice points, all on the BASE-12 Cartesian plane. So now what we're going to do is just take this information and progress through the pattern. We're going to go to the fourth ring of the dodecagon pattern, and that's what I've got up here. So we're going to go to where the 1, 2, 3, 4. So basically we multiply everything by 4. So 4 times 0.96 is 3.2 root 2. So we can just look at this and expand on it. So this radius will be 3.2 root 2. There will be 4 sections of 0.96. So something like that. 1, 2, 3, 4. Those are all point. And then this section here is going to be 4 sections of 0.5 root 2. So we do the math in BASE-12, we get 1.8 root 2. And we go through the same procedure of putting our compass on this point, setting it to that length, transferring it down here, and redrawing a circle. So these circles overlap each other. They're going to look something like that. So we have 2 big circles that overlap each other, and I'm going to show you what that looks like from a page in my book, just so you can be clear. It's a very simple process. I hope that you can understand that. And so now we do something that's very, very interesting. Now what we do is we draw circles on these points, centered on this point. Again, a lattice point. It's going to look something like this. So we're going to draw a circle there and a circle there. Where do these circles come from? These circles have a radius of 0.49 root 2. So if you remember, that's the radius, or that's half of 0.96. So these circles have a diameter of 0.96. So what we're doing is we're taking the diameter of our circle, we divide it into sections of 0.96 root 2, again defined by specific lattice points, and we're placing it on initially the 4 corners, because we have the same thing happening over here and down here and over here. So that's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're taking the diameter of this circle, and we're dispersing it around the circumference of this, well, around the perimeter of the dodecagon one time. So 8, putting it in there. So now we've Now we want to again do the same thing here. So now we're going to draw a circle defined by these points. So we're going to have one that's going through the center like this. So we do the same process of setting our compass to that length. So it's going to have a radius of 0.5 root 2. Bring it down here. We make marks on here and there on that same circle. And then we do the same process of doing circles like that. Again, same radius of 0.49 root 2 with the diameter 0.96 root 2. So now we ask the question, what's the space between those circles? So we have the distance from the center here to that was 0.5 root 2. The radius of the circle is 0.49 root 2. So remember, we're in base 12, so we subtract one from the other. So we get a distance of 0.03 between the center here and this center line. So this gap right here. So on the other side, it's the same. So you multiply that by 2. So the gap between these two circles is 0.06 root 2. So this gap here is going to be the same, 0.06 root 2. So now we're doing that all the way around the entire diagram. One division of the diameter into the circumference on these corners. Now you do it 2 more times for here and here. So we've placed a total of 8 times 3 is in base 10. It's 24. Base 12, it would look like 2 do. The space between is 0.06. Now this, let's look at it pairs. That pair, that pair, that pair. So it's going to be 0.06 times a dozen. So again, a dozen equals 6, or 0.6. Okay, so 0.06 times a dozen, looks like 10, gives us 6 root 2. So now the question is, what's happening here? What's the space between these two circles? We know that they're centered. We know these larger circles are crossing over, they intersect each other, and that's going to happen right on the 30-degree line. We know that everything's centered or balanced on the 15 and 45, so we're moving, everything between these going in the same direction is going to be balanced on the 30-degree line. What's the distance? So let's just do a quick little catch up on the math here. The total perimeter, let's just see here. The total perimeter of the fourth ring is 5 root 2 times 4, so 1 do 8. So we got, this is one section, multiplying that by a dozen, 1 do 8. So I'm going to write that over here, 1 do 8. We divided this length of 3.2, so the total, that's the radius. So the diameter is 6.4. So that times 2 equals 6.4 root 2. So we did that 3 times. 1 do 7 root 2. So we subtract that from there. We get 1 unit of the square root of 2 remaining. And so that's what all the gaps are. So when we added all these up, we get half a unit of square root of 2 minus 0.6 root 2. So we have half a unit left. And we have an equal amount of spaces between these two circles. So there was 12 of these twins, so to speak, and then there's 12 left over. So given that the total perimeter of the base 12 dodecagon on the fourth ring is 18 root 2. Given that we spaced the 17 root 2 equally by dispersing these circles all around the circumference. We had the gap between them totaled half of unit of square root of 2. We have half remainder. Therefore, this space here is also 0.6 root 2. All these circles are on the same, all these smaller circles, units of diameter on the same circle. There's the balance between the degree lines. Therefore, this 0.6 root 2 is the distance between here. So again, the same thing, either side of the 30 degree line is going to be 0.0303. All right, so essentially what we've done is created a 24-sided polygon by connecting all the center points of those 0.49 root 2 radius circles. So now what we want to do is calculate the angle inside all of those circles. So we can do that by using this formula n minus 2 times 180 divided by n, where n is the number of sides of the polygon. So, on the base 10 side, it's 24 minus 2. We go through that calculation and we get an answer of 165 degrees. So we can do the same calculation on the base 12 side, where n minus 2 is the n is going to be 2 dozen. And this 130, I don't know if I said this yet, but in base 12, this number is called a grow. It comes from a gross, which is 144. So this number is 1 times 144, 3 times 12, if we were to convert it back to its base 10 version. But now it's pronounced 1 grow 3 do. So 2 do minus 2 gives us 1 do dec times 1 grow 3 do. We get this number here, we divide the 2, we get something that looks like 119 in base 12, but it's actually 1 grow 1 do 9. So that's this angle here. So what we want to do is find out the angle that in this little triangle here. So what we can do is simply divide that in half. I'll do it in base 10. So 165 divided by 2 is 82.5. So that's this angle right here. So now we want to figure out this angle here. So we know all of the angles added up is going to be 180. So basically 90 minus so I guess our angle theta there is 7.5 degrees, 7.5 degrees, doing it all in base 10. So we could also calculate that simply by dividing 360 by 48. So we've got 24-sided polygon. Each side is the length of 10/12 or point dec root 2 in base 12. So we divide that in half. We got each triangle is each section of the polygon is 2 triangles sort of back to back. So we have 48 triangles. So that same calculation in base 12, 2 grow 6 do divided by 4 do equals 7.6 degrees. So that's the base 12 version. Basically, it's the same, 7.5, 7.5. Everything's pretty equal there. Not a lot of decimal places, but that's the 1.5 and 0.6 do line up on the Cartesian plane in base 10 and base 12, the actual point. Okay, so now what we want to do is approach all this geometry from the base 10 trigonometry point of view and just check out what our triangle, how that angle works out, what we get when we look at it from a trigonometry point of view. We've now built this entire diagram using base 12 math, base 12 geometry, base 12 Cartesian plane. I think I've created a strong argument that this is a solid geometric pattern and that's the right answer. So now let's just look at that from a trigonometric point of view and see what we get. So when we divide, so again, we got, the short side is 5/12. So when we divide, you can sort of cancel out the square root of 2 and just work with our fractions because it's equal all the way around. So 5 divided by 12 is 0.41666 repeating. 19 divided by 6 is 3.1666 repeating, so we're going to divide that into that. And we get an answer 1315784, etc. So that's the answer to this question. So now what we want to do is use our tan or cotangent. Basically, we would just use our calculator, punch in all these numbers, and the answer that we would get is 7.495857, and it goes on. So that's not exactly the same as that. So now we have a little bit of an issue or a problem or a challenge or something's going on here. One of these answers seems to be a little bit off. So we've looked very closely at the geometry in base 12. How close are we down here with our calculation in base 10? How do we get these numbers is the question. We put our, we calculate with our calculator, we get an answer. How well do we know what our calculator is doing? Well, first of all, it's using this number right here as part of its calculation and this number right here. And how precise is this number in representing 5/12? And I would say the answer is not so precise. 0.5 root 2 is precisely 5/12. It's just one division of the length of 1 into 12ths. But here, when we transfer or do the calculation of dividing 5 by 12, there's a step in there where we first divide everything by 10. We divide everything by 10, and then we add 4 of those tenths, and we see, oh, there's still something left over. So then we divide that remaining area by 10, or by 100, or no, by 10, and then that creates 100. So we add 1 100th, and then 6 1,000ths, and we keep adding groups of 10, exponential groups of 10 to get this number, and we don't go to infinity. Apparently, if we take it to infinity, then we reach 5/12, but we're not taking it to infinity. We're taking it to 9 or 10 decimal places, and then that's as far as our calculator can go. And the same down here, just to give us, to be clear, we put in a lot of numbers. We put the max out. We max out our calculator. And that's the answer that we get. So we get a length that's almost, but not quite. So we have a triangle, but that's almost, but not quite 3 2/12. We have a short side on the right angle that's almost, but not quite 5/12. And so then we get an angle, theta, that's almost, but not quite 7.5 degrees. So in a sense, we're getting the right answer because we're using slightly shorter lengths and we get a slightly shorter angle. So we could say, well, given the fact that we can't really access a precise version of 5/12 in base 10, we get the right answer, but it's not the right answer as far as saying, well, is this, we lose something in between saying 5/12 and 3 2/12 and 0.5 root 2 and 3.2 root 2. Something's lost in translation there, and one of these is a little bit off. We don't get our, we don't get 7.5 degrees. You get 7.49. This is the official answer right now. If you go to any math textbook and punch in those numbers, you get that. You get a check mark that you got the right answer. But I'm saying it's not precise, and I think it's acknowledged in base 10 math that a lot of these answers aren't precise. The fact that we got all these decimal places, it's precisely all those decimal places. So there's some controversy there. I'm going to leave it at that. Just want you to be aware that there's going to be some pushback. Right? We want to figure this out. Who's right? Which of these triangles, which of these methods of analyzing that triangle is the perfect method, and which one is close but not exact? Okay. So what we're going to do now is continue our process of analyzing the base 12 version of this diagram on the base 12 Cartesian plane. We're going to look a little more closely at the geometry that we've created around the circumference of the circle, and then we're going to push out into the second, third, and fourth rings of the diagram as we begin to build and construct the diagram for 360 degrees, or 2 Do, 6 Grode degrees in base 12. All right, so now I'm going to go over the steps that we need to take to actually build the diagram and just share with you how it evolves and grows. So basically becoming aware of the mathematical structure or layout of the overall diagram. We've now established the most important element, which is the ratio between the diameter and the perimeter, which becomes the circumference of the circle. But the perimeter of the dodecagon, or the polygon, really, it's now a polygon, and it just becomes a more and more multifaceted polygon. But all of the sides are always, all the sections are always the same length of point dec root 2, which is 2 long skinny triangles, either side of which has the short end is 0.5 root 2. So we're basically, that's the structure right there. We've got that ratio. Now we just want to look at how that evolves and what it looks like as we build the diagram. All those triangles, it gets larger and larger and larger. We're going to come back to all those triangles in a little bit, but first I just want to go over this procedure so you're sort of familiar, with what it is that we're doing. So we drew our initial 3.2 radius circle, and then we added 0.5 root 2 at a 90-degree angle, and drew another, where's my 45 here, at a 90-degree angle, drew another circle, and then we added point dec root 2 for a final circle. So there's 3 circles which define that first ring, and so we're going to do that with each ring of the diagram. We draw 3 circles, one where the 45-degree line is crossing our circle with the radius that's now in units of 3.2, 6.4, 9.6, Do 0.8, and so on. And then we have the 2 next points going up over 0.5. Those points, again, lattice points, draw that circle. And then these 2 on the outside going over and up over the length point dec, and then drawing that circle. So each ring, I call them primary rings in the book, is made up of 3 circles. Now we've already established our 0.49 root 2 radius circles and our larger unit circle, which I call the UOC, unit of circumference. So this is what it looks like. This is the circle that is anchored on our main circle with the radius in units of 3.2 root 2. And then these smaller circles are the circles that are anchored on our middle circle, and then the edges of this are defined by our outer circle. So those are the 3 rings, and they're all connected to this geometric structure. So there's a few options that we have now in terms of growing the circle. The first thing that we can do is we've got these rings, our primary rings, and we've got our degree lines going out. So you can see that every ring of the diagram has a unit of circumference on the 15-degree lines, the 45, and the 75. So we can do that next. Just go along, put our compass on the spot where the degree line is crossing the appropriate circle, and just draw our large circle. And if we wanted to, on each of those, we could set our compass to the 0.5 root 2, draw a little circle to get those 2 points. But there's another way of doing that, and I'm calling it paralleling the degree lines, where we basically, now that we've got these first 2 circles established, and remember, this is a circle, so we have the same thing going on the other side. We can draw lines through these circles, connecting on the other side, and we're just going to parallel our degree line just like that. So there's a gap here of 0.5 root 2 on either side. So we've got like a section. We create a perfectly straight section. That's a facet of our polygon, and we're able to then that intersects all of our second circles in each primary ring. So right away we get all those points, and we can go around and draw those 0.49 root 2 radius circles. And then we can do the same thing for the outside. We have our outside points on the 3rd circle of our primary ring, so we can draw a line that connects all of those, and we get these nice thick degree lines that have an overall thickness of 1.8 root 2. So I'll show you some pictures of that from my book just to give you a clean picture of what that looks like. And so that's every ring of the diagram, every primary ring. Then you'll notice the line going through here, the degree line going through here, and then it hits. Now we can do the same thing with the second ring. Is we're basically doubling the amount of units of circumference. Here we have so these are still degree lines that are generated by our Dozenal Pisces diagram. So we can draw these now and then do exactly the same thing. We're positioning them on the primary, here it's going to be 6.4, 9.6. And then we can do this. And now we can also use that same paralleling the degree lines, but we're sort of using half of this one, the same one that was here. Now we're just jumping over here. Again, we've got another facet of the polygon, and we can do that. So we're going to go through, goes between two rings through one, and then up here it's going to go between that one and this one, and then hit there again. So you can draw it there, and we draw it through here like that. We do that there. So here these parallel lines are going through, so we can do the same thing, but we realize now we're going to be we don't have our degree line for that, but we're generating the 0.49 root 2 radius circle. So the key, or our main priority for the diagram on each ring, is to find the positioning of these small circles. That's the main thing. If we can get all those on it, then we can choose which gap we want to put our compass and draw the larger circles. Find the pattern in between. We could draw one here. We've got single circles, or we could put it there, and then we have sort of a regular pattern. So we kind of have options depending on how we want to arrange our units of circumference. So that's the main priority. So given that, once we find all of those circles, the next thing that we want to do, as I was just showing or illustrating, is we want to find the midpoint between them. Sometimes we get those circles, then we need to generate the degree line that goes between them to generate new degree lines as the diagram expands. So the way that we do that, you'll notice that I have secondary rings here between each primary ring. So in the book I call them the secondary rings. And you can see here what I do is I draw a circle on the compass. You put our compass on that radius, so that's the circumference of that circle. We draw these, and these overlap quite significantly, so they create 2 points, and that basically creates the midpoint between the two circles. So if we have a degree line going through here and a degree line going through there, we can put on our secondary ring, we put the circles on those degree lines, and where they overlap, we'll create the new degree line splitting those 2 points. And we can also use that same method for locating a point. If we have two of these, we want to find a midpoint, we use that same method. So this is called finding the midpoint, where we basically draw 2 circles on our secondary ring, and where they overlap, we find the midpoint between those 2 particular degrees. So that's another method of creating more angles and degrees within the overall structure of the diagram. And so another method or pattern that emerges is when we do this paralleling the degree lines and we run our lines out, we have all these degree lines on either side. We take that point, I'll use this 4th ring as an example. So we have a parallel line that goes out to this point, we've generated that. Now we put our compass or our straight edge, we draw a line from there to the center. So now we create a really long, skinny triangle down to the end, and then that continues out. So this is the 4th ring. So on the 8th ring, this line that went through here, through a 0.49 or 2, the next ring, it'll go between. So on this 4th, then the 8th ring, it'll go between 2 of these smaller circles, and then on the 12th ring, it'll go through another one. And we see this pattern emerging right away with these circles. We go through here, then you notice it goes through a 0.49 root 2 radius circle, and it goes between two of them right here, and here it comes through and it goes through a circle here, and it goes between them, and so on. So it's kind of weaving its way through. I'll show you some pictures of that now from my book. And again, here that's the shortest version. Every basically second ring it intersects a small circle, and then that pattern gets longer if it goes to the 4th, 8th, 12th, 5, 10, 15, and so on. So all of these patterns initially start quite close and repeat quite quickly, but then as they begin farther away, the repeating process goes farther and farther as the diagram gets larger and larger. So in a sense, that's essentially it. Those are the three main patterns that I discovered that are within the structure of the diagram, where you can build on the degree lines that go before to create more degree lines. That's basically what we're trying to do, is grow the circle in a fashion where everything remains balanced, and you have to do it like that. You have to work on what you've already got. But that enables us to build on the initial structure of the Dozenal Pisces diagram, and we're not just splitting everything in half. It's more than that. And we can divide the circle into these angles into thirds and fifths and sevenths. And some of them are a little bit, you have to combine those techniques, like the 7th and the 11th. Kind of like the prime number rings are a little more complicated. The patterns don't line up so easily. Like there's a pattern with the 2, 4, 6, 2, 4, 8, 16, that kind of thing, and 3, 9, 12, and some of the patterns merge. So the patterns merge on the 15th ring and then on the 30th ring. So that's what generates, they all sort of come together, and there's multiple like parallel lines and degree lines all going through similar places. So that's something you have to get the book to see, because it happens quite a long way out in the diagram. And that's one of the challenges. It's such a large scale diagram. I'll just show you a picture here. I built this in my basement at the end of 2020. I wanted to see what it looked like. And this construction is basically 2.5 sheets of plywood. So that's 20 feet long. And that's only 15 rings. That's half of the distance. So it's only a quarter section. So the whole pattern is quite huge. And I would love to see a mural of this somewhere where you can just lay it all out and have all the lines go out and see the full 360 degrees, all the circles and the full 30 rings, and then the full complete diagram built, and just see what that looks like. So ultimately, it would be great to have a computer program that was built in units of, that was a Dozenal geometry program where we could work with this and then build on it more. So I'm going to stop there as far as the structuring of the diagram and the instructions for building it. I'll maybe show you a few more pictures of what it looks like as we approach the 15th ring and the 30th ring, just how those repeating patterns sort of emerge as the circle gets larger. Okay, so I've spent a lot of time explaining how we create the diagram and looking at the geometric structure, sharing that information with you, showing you how it grows from ring to ring, and the degree lines sort of open up, and then we fill in the gaps and keep growing and all that sort of thing. So now I just want to look at the angles that are emerging from each ring of the diagram as we progress, as we're drawing those degree lines and separating them and connecting all the dots, the lines, the polygons. What are the degrees that are actually being generated from our diagram of 2 grow 6 do degrees. So let's start on this side. I showed you the formula, the n-2 times 180 or 130. So I'm just going to show you the answer to that equation. So we're looking at here's our polygon, our section of polygon. We're looking at this angle. We went over the very first ring. So the second ring, using that same formula, we get 172.5. And I'm going to go through the base 10 side because that sounds more familiar. That the circle kind of opens up, or those angles open up quite quickly in the first few rings as it grows fast, and it kind of starts to flatten out very fast. So we go from 165 to 72, 175, a 10-degree leap right there. Then it's 176 and a quarter, 177, we have a few, 177 and a half. Then we get into 178 all the way through here. Here's a half there. And then 179 degrees is our 15th ring. So that's 1 degree from 180. And then the next 15 rings, we open up just half a degree more. There's a whole series of circles in there in different, much smaller increments. So I give you that whole table in the book, and you can see the same thing on the base 12 side. You have a repeating decimal here, but on this side it's 0.4, half is 0.5, here it's 0.6, 0.75, 0.9. That's what that all looks like. 1 grow 2 do L 0.6 is 179.5, so it's all the same. Basically, the growth pattern is the same. So on this side, we're talking about the degree on the inside, around the center, and we've already figured out the first angle there is 7.5 degrees. We use this formula, 2 grow 6 do divided by 4 do. And so these numbers are coming from the division of each section. So we have our unit of circumference, and so we know on the first ring, we're dividing this, there's going to be one of these units of circumference. In the next ring, there's going to be 2 of them. Then in the next ring, 3, then 4, and so on. And so each of these further divides our diagram into quarters, to 4 sections. You can see how that works. And so here it's 4, then it's 8, and then it's a do. So this is where these numbers come from, 4 times a dozen. And then again, there's 10 of them in this, a dozen in the first ring, 2 dozen, 3 dozen. So we have 4 times 10, 4 times do, 2 do, 3 do, 4 do. That's where we get these numbers. And then it's just simple, math adding up. Here's 1.5, 1.3, deck angle, 0.9 point deck, 0.76 on the 12th ring. Here we had 7.6. And how well do you know your base 12 math now? 76, 7 do 6 is 90 degrees. So we divide our 90 degree by 12. You get 7.6, divide that by 12, you get 0.76. You see a lot of that in base 12. The 2.5 degrees to 30 degrees to 360 in base 10 is 2.6, 3.6, sorry, 2.6, 2 do 6, 2 grow 6 do. So in base 12, there's a lot of just moving the decimal around instead of very different looking numbers. So that's just something to, again, remember or to keep in mind that it all fits together like a beautiful jigsaw puzzle, just pieces all meshing with each other when we approach the geometry of the circle in base 12. And you can see there's some interesting patterns again throughout there. So that's the 12th ring, then we go to 15, then 30. So the last ring of the diagram is our 1 degree. This is like a 1 degree section. So one of our units of circumference fits inside a 1 degree, and then so it's further dividing that 1 degree into quarters. So we have 0.3 degrees is how fine the 30th ring of the diagram divides our circle completely. So that's really, I would say, in a sense, that's the end of the diagram. But on the other hand, no, we want decimal places in there. So we need to keep going and then really stretch it out to get, to further divide 1 degree into, the third. So we get 0.1, and then kind of keep going. So it's a long, sort of stretched out process to do it precisely. But of course it's possible. And this is where we're looking to eventually get computers in base 12. AI should be programmed in base 12. Now's the time to do that. Get us some geometry programs as well. And if you have my book, at the end I introduce another geometric Cartesian plane structure that I'm not going to go to in this video, but if you get my book, there is more information at the end that I'm not going to go into in this video. Now that's enough of the 360-degree structure, 2 grow 6 dough structure. Now we're going to look at the equation that's kind of lurking beneath all this, the actual dividing of the diameter into the perimeter. Okay, so the numbers that I'm choosing to do the equation are the ones that originate from the first ring of the diagram, where we have a diameter of 1.7 root 2 and a perimeter of 5 root 2. So we're going to be dividing 1.7 root 2 into 5 root 2. So we're going to convert those into their square roots. We're going to do a square root version of this equation. So we've already seen that 5 root 2 converts into the square root of 4 dough 2. Looks like 42. And the 1.7 root 2, we square that. 1.7, get 2.61. And the square root of that multiplied by the square root of 2 gives us the square root of 5.02. So that's what this looks like. You can see it's a long division equation. It's quite straightforward. What I did was write out all the factors of 5.02 just so I could work with them in the process of doing the equation. You can see it basically we're just multiplying and you get the answer. You subtract regular long division. Very easy and straightforward. The only challenge is that it's in base 12, so it takes a little while. I have downloaded a base 12 calculator, so I can use that to help me do the math. And so we have a square root answer. So that answer you can see right there, 9.L80171941674679410921116, and it keeps going. So what's interesting about this number, it does keep going, but eventually it repeats. So it goes for 9 dough 6 iterations. So we've seen that number already, 0.96, 9 dough 6, etc. So that's the amount of units between one section of the dodecagon and the next one as we travel along the radius or the diameter. So that's interesting that those two numbers merge, that this number, which is exponential, remember each of those numbers is multiplying by 12 or dividing by 12, however you want to go. And so there's an interesting relationship there right away. So I'm just going to talk a little bit about some of the other interesting aspects about this number, and they are all in my book. All this information is in my book that's available on Amazon. Just reminds you what we're looking at here, the Understanding Base 12 Math, how to draw the perfect circle using Dozenal geometry. So the interesting thing, there's patterns in here. So the base 10 version of pi is known for having no patterns and being completely random, and that seems to be one of its strong characteristics. So here we have a number. If I write it out, or you write it out in rows of 12, if you do that 9 times, you go 9 rows and then a half, there's the 9.6. You'll notice down the right hand column there's a combination of numbers. I'll show you what it looks like. Again, I put it in my book for you to look at and kind of study and meditate on, because you can see that there's a pattern going there. We have a progression of numbers, 1, 2, 3, 4, 5, but some of them are pairs. And then I decided to just write the whole number out again, starting there and continuing, and then I saw that the rest of the numbers, the pattern just kept going. And so we have a complete sort of string of numbers there that is enmeshed or weaving through this long string. When you have a long string of numbers like this, it's hard to tell where the patterns are, but arranging them in those columns. So there's something, again, within the 12ness. And then if you look closely, I'll show you the full picture here of that number down the center column, or the sixth one from the left. The same pattern emerges, but sort of halfway through going around. And then I realized that actually this pattern is similar, not exactly the same, but it's similar, runs through every column, but it's staggered, whereas every 8th number, or 8th, or 9th, or 7th, and then there's 11th, so each column has its own pattern, where you go through and you write down one number, then you count 8, and then you write down another one, and then you count 8, and just kind of keep looping through the column. You'll pull out more and more of these strings of numbers that are sequential, but have a little bit, there's pairs in there too, and they're not all the same. So I found that really interesting. And I think actually I'm just going to leave it there. We got a number here that has a lot of interesting qualities, but it's not the same as the base 10 version of pi. So it's obtained by dividing the diameter. Ultimately, if we look at the finished product, we have a huge circle with literally, millions and billions and trillions are too small for the number. It's literally a Google. We do the process, over 100 times of dividing into the diameter into the circumference. So that's how many points we ultimately get, and they're all, if we had a computer, we would be able to do it in such a way that we use the diagram that we just created, and we're able to plot all those points, and there'd be a space between them all. And I think it's interesting to think and just to realize, all through the process of creating the diagram for 360 degrees, or for 2 grow 6 do degrees, we're only ever dividing the diameter into the circumference 3 times. We're never adding any extra length. We're just doing that, and then the extra, all those decimal places are simply the empty space. We're by cutting things up smaller and smaller and sort of squishing those 2 lines together, where one defines the positioning of the units of diameter and the other one is our actual circle, and kind of pushing it together, we create more space somehow, but it's all in the decimals. So it's always just 3 times and then all the empty space, and that's what makes up our value of pi. But again, it's dispersed throughout the circle, so it's perfectly balanced and symmetrical. It's not like a lump with a big space at the end that we keep adding on solid bits to. So it's a very different model than what we currently have in base 10. So that's the square root version. And then we got to just think about what's a square root. This is the result of squaring another number, just like square root of 9 is 3. So when you see the square root of 9, you go, well, what number multiplied by itself gives us 9? And we know it's 3. So here we have this long number. What number multiplied by itself gives us this number? Will give us just the straight number 9.L801, this huge number. Where does it come from? What number can we square? So in order to find that out, what we're going to do is do the same equation again, but we're going to knock off those square roots and just do 5 divided by 1.7 and see what type of number emerges from that equation. So we're dividing 5 by 1.7. I'm going to pretend I don't know how long the number is. So that's interesting. We got a 3 to start. So far, so good. Okay, 3.1. So that's it. Now we can see it's going to repeat. And that is the base 12 version of pi. So I think we ended the last section by saying, what number do we multiply by itself to get that long version 9.L8017191? It's going to be this number here, 31 dec 8 dec 1, 31 dec 8 dec 1. So we can see it's repeating, but it doesn't have to repeat to infinity. So the other number went for 96 digits before it repeated. So I think that's enough. I think that one complete, and I could be wrong, but that one complete sort of run through of the whole number is enough. And I'm always thinking in the back of my mind physics. Pi is a part of physics. So that whole number to me is the number that takes us from the quantum realm up into the edge of the universe. And And so that's where the empty space is sort of throughout. The empty space is actually connected to the empty space that's in everything that we know, in atoms and molecules and quantum quarks and all that kind of stuff. And so we don't need to, this number doesn't have to go to infinity, that number doesn't have to go to infinity. But we would take this number a certain amount, a certain length, and then multiply it by itself. If we just multiply this by itself, you get a shorter number. It would start off 9.L80, and then it would kind of deviate from that number. And the more iterations of that pattern you have, the farther along you would go with the number that we just were looking at in the previous section. So that's basically it. And I'll be honest, when I calculated that the first time, it seemed kind of disappointing in a way, because it was like, that's very short. We're so used to this really long number. But upon further reflection, again, it's about patterns, and the fact that the other number has no patterns. We're looking for patterns. We're looking for structure within math, within the building up of things, within the interrelationship of things. Having a number that ends and repeats gives us bounds for our sine wave. You know, pi and trigonometry, sine, cos, and tan, those are waves. You know, pi goes up and down. To have those bounds suddenly opens up, and having individual units with space around them. Calculus seems to be all about finding, like going into infinity, trying to find what's happening at a very small specific spot. So now we're going to be able to look in there and have a small point with some space around it, and really get to the heart of a final bottom, and then work our way up again, and instead of just getting lost in infinity. So this is the advantage. Although when I say advantage, it sounds like I've created a new vacuum cleaner and saying the advantage of this new vacuum cleaner is it does a better job. It's not. It's like the real number that would work. This ability to divide things up into smaller units and have some space around them connects with the real world. So the advantage is it's the right math that I think actually emerges from physics. It's not the other way around. It's not a math tool that we're creating to study physics. It's the math that emerges from physics itself. So that's the base 12 version of pi right there. You square that, you get the other number. You can do 2 pi. You can divide this by 2, by 3, by 4. Maybe I'll do that right now. All right, so I divided that value of pi by 2, 3, 4, 5, 6, 7, 8, and 9. And as you would expect, the result is repeating decimals also in so 6 units, and then it repeats. There's some patterns in there. This 958,263 or 9, shows up here, here, here. Here, the version of pi itself shows up here. 4507. Yeah, 2 and 3. It's a lot of similarities and a lot of just weaving together of numbers and patterns. If you think about, say, squaring the circle, and you want to square, so we got 4 sides. Pi divided by 4. That pattern's going to fit in there. And again, it doesn't have to go to infinity. There's a point where it stops, and everything's just going to fit together and be done. The spaces between the points will all line up and everything makes sense. So there you go. That's the version of pi. I feel like I've fulfilled on my promise at the beginning of the video. I introduced you to the difference between base 10 and base 12. I explained how that all works. I showed you how to build a Cartesian plane using the Dozenal diagram, and how we create squares that are divided into twelfths, a 1 by 1 square. I introduced you to the base 12 dodecagon pattern, explained how it works, and I showed you how to use that pattern to create the diagram for 360 degrees. We did a pretty deep dive or thorough explanation, I feel, of how to create the diagram for 360 degrees, or 2 grow 6 do degrees in base 12. And then I finally gave you the value of pi that emerges from that diagram, from that geometry, just dividing the diameter into the perimeter. You get the square root version and this simple 3.1 deck, 8 deck 1 repeating pattern. So that's a lot of information, and there's a lot more to go. As you can imagine, it's a huge diagram that ties in, the 45 degree line and the 30 degree line, those triangles. it's just everywhere throughout the Cartesian plane. There's a huge amount of more math to be discovered in base 12 with all this geometry, and so I hope I've inspired you to look further. Right now, I have another video ready to go, or the topics are ready to go in terms of the Fibonacci sequence and the Pythagorean triplets. Actually, this base 12 dodecagon has a connection to the Pythagorean triplets. So I'll just point it out right away. The very first ring, the circle with the radius of the square root of 1.21. That circle actually has 12 points that define its location on the base 12 Cartesian plane, not just 1.1 on the x and y axis, but you go over 1 and up 0.5, and then up 0.6, and then 0.7 is where the dodecagon lands. I would explore that if I was you. There's a whole bunch of stuff there with Pythagorean triplets, and again, the Fibonacci sequence in base 12. Patterns emerge. I've made some introductory videos. You can check those out. But for now, I think that's it. If you want to support me, you can go to my personal website, ericlarsonart.com, and buy some base 12 merchandise or Dozenal stuff I'm selling there. You can buy the book, and or just whatever, spread the word, talk to your friends, introduce this information to other people, and let's just keep going here to really get this information out there. Because if mathematicians are going to love this once they realize there's actually something here worth exploring, I believe that. And I think for physics, this will help unblock the logjam which seems to be happening right now. Solves a lot of problems with regard to infinity. In my book, I touch on that at the end, where this leads, the structure of that unit of circumference that I showed you. It's a lot of good stuff. Thanks for watching. See you in the next video.